In this video, I'd like to talk about something called recursion. Now, recursion is the idea of a function that calls itself. Now, a really classic example of this is something like the Fibonacci sequence. So the Fibonacci sequence, if you're not familiar, is this set of numbers here: 1, 1, 2, 3, 5, 8, so on and so forth, right? This sequence of values here, each number is the sum of the previous two numbers, right? So you start with two ones, and then the next number is 2, 1 plus 1, and then 3, which is the 2 plus 1, 5, which is the 3 plus 2, 8, which is the 5 plus 3, right? So on and so forth. And this chain of numbers continues on forever, right? This is the Fibonacci sequence. Looks something like this. Now, the Fibonacci sequence, one way that you could write this mathematically is you could say the Fibonacci sequence at a value n is equal to the Fibonacci sequence at n minus 1 plus n minus 2, right? This is why this is a classic recursive problem. This function is defined based on the sum of two other calls to this exact same function, right? So when we want to figure out what the Fibonacci sequence of 4 is, we would say, well, that's equal to the Fibonacci sequence of 3 plus the Fibonacci sequence at 2. And then we'd ask ourselves, well, what's the Fibonacci sequence of 3? Well, the Fibonacci sequence of 3 is equal to the Fibonacci sequence of 2 plus the Fibonacci sequence at 1, right? And so on and so forth. That's what this value is. And then 2 would become something else, right? And you can kind of see how this mathematical function is recursively calling itself, right? And we can kind of expand this as we go down and determine what all these sort of sub-functions are, right? In the same way that we can define a regular mathematical formula to be recursive like this, we can do the same thing with a function in code. So we could write a Fibonacci sequence function that looks similar to this. I'll write a Fibonacci sequence function. It's going to take a value n. And I would say that this function, if n is equal to 1, or if n is equal to 2, then the value is just simply the number 1, right? These are the first two pieces of data here, right? The first two values here, this number 1. Otherwise, this value is equal to the function at n minus 1 plus the function at n minus 2, right? And calling this function with a value of 4, just like we've written up here, calling this value the function of 4 will return the Fibonacci sequence of 3 plus the Fibonacci sequence of 2, right? And this works in code. You'll actually see this function call itself multiple times, just like I started to expand this one here, right? Now, you could also solve this not recursively. You could solve this iteratively, meaning using just traditional for loops by keeping track of 2 or 3 variables in this case, where you'd have like a current value, a previous value, and then like a second previous value. And then this one is sort of incrementing your way up as you loop through this for loop, right? But this function here is just much more easier to read. It's more elegant. It's not more efficient though, which is one thing to note. So why do we use recursive functions? Well, we use them for a couple different reasons. Recursive functions, there's a few things to know, right? They're not always faster, right? But sometimes they are. And it can make for cleaner code. It can make for cleaner code. That's another reason why we'd use them, right? And also, some problems are just like naturally recursive. So this Fibonacci sequence here, this one is sort of like naturally recursive, and it makes a lot of sense to write this function in this recursive way, right? So sometimes they're just plain easier to write. Now, there's three rules that you need to keep in mind with any recursive function as you're writing these things in code, right? Here are the rules for recursive functions. 1, they must have a base case. The base case for a recursive function is when this function stops calling itself. So in this Fibonacci sequence function, if n is equal to 1 or 2, then it's just going to return the number 1. So that is the base case for this Fibonacci sequence function. If we don't have a base case, that means that this function will just repeatedly call itself over and over and over again, and we'll essentially end up with infinite loops. So we don't want that. So we need a base case is the first thing. Number 2, we need to converge on the base case. This means that whatever data that we're operating on needs to get closer and closer and closer to our base case. In this Fibonacci sequence example here, our data is the value of n. And every time I call it, I subtract 1 from it or I subtract 2 from it. So this value of n is getting closer and closer to our base case of 1 or 2. I pass 10 in here, and then this is going to call Fibonacci with 9, and Fibonacci with 8, and so on and so forth. It's going to get closer and closer to this base case. So number 2 is the data needs to converge on the base case. And then finally, the third rule is it needs to call itself. Recursive functions naturally call themselves, and if they don't call themselves, they're not recursive. So there's a very quick overview of recursive functions. They're not always faster. They can make code clean, and they can be sometimes easier to write. The 3 rules: they need to have a base case, they need to converge on the base case, and they need to call themselves.